Good morning, everyone. It is my pleasure to welcome you today to this latest in a series of webinars hosted by the SAIMM over the last few months. This has really been a great initiative, I think. I've never had such an opportunity to listen to such a diverse range of talks presented by very knowledgeable people. So it gives me great pleasure this morning to present today's speaker, Dr. Laura Kuhar. I have known Laura since the beginning of her career at De Beers, and I'm really happy that she agreed to give us this talk this morning on this fascinating topic of in-situ mining. Laura is a research team leader in the Syra Minerals Group in Perth. She and her team are working towards the vision of an invisible mine with research into in-situ recovery. This is a bit like keyhole surgery for mining, and it involves the injection of liquid underground, dissolving the value metal and processing the fluid at the surface. This goes without any costly mining and rock processing with potential environmental benefits as well. Laura has an undergraduate degree in chemical engineering, a PhD in chemistry, and has been with the Syra for 11 years. Before that, she spent some time as a researcher at Anglo American and De Beers Consolidated Mines. Laura is also very active in promoting science and engineering amongst young people. She's one of Science and Technology Australia's 60 superstars of science, technology, and mathematics. And she has won awards for science communications from the South African Agency for Science and Technology Advancement and the American Association for the Advancement of Science. She has also published almost 50 publications. So having known Laura for a long time, I know she's an excellent speaker, and I'm really looking forward to hear about her journey towards the invisible mine. Laura, you can share your screen and start when you are ready.
Thanks, Leon. Thanks very much, and thanks for the lovely introduction. Yes, we certainly go back a number of years. Don't remind me how old I'm getting. So I'll just share my screen. Give me a second. All right. Well, thank you again for the invitation to present today. I see a few familiar faces on the participants list. And as Leon mentioned, I go back quite a few years to De Beers and Anglo in South Africa. And it's great to be speaking today. So I'll be talking about in-situ recovery and the invisible mine. But just before I kick off, I wanted to let you know who the CSIRO is in case some people are not familiar with the organization. So the acronym stands for the Commonwealth Scientific and Industrial Research Organisation, and CSIRO is essentially Australia's national science agency. We've got about 5,500 staff across the world, mostly based in Australia, but also in Singapore, Vietnam, America, and Chile. We've got 57 sites, and the value that's delivered to the Australian economy through our science and technology is estimated at $4.5 billion a year. Now, our research focuses on 9 core areas: animals and plants, astronomy and space, climate, environment, farming and food, health, IT, mining and manufacturing, and renewables and energy. And I sit in the mining and manufacturing space. So I'm based in Perth, and I'm actually in the processing group. We've also got an exploration team in Perth. So they essentially find the rock and we look at ways to process the rock. So I'm going to talk about in-situ recovery today, and also the research that we've been involved in, are currently involved in, and some of the exciting projects coming up. But before I do that, I'll just give you some of the background and explain the concepts, because we found that many people are actually unaware of this technology. So many of you will be familiar with this sort of image, a large open pit. This particular one is located in America. It's an open pit copper mine. It's the world's deepest man-made open pit excavation. So it's 4.5 kilometers across and over 1 kilometer deep. And it's been in operation for over 100 years. So what really struck me is that there was a comment made that if this open pit were a stadium, it could seat 9 million people, which is quite a mind-boggling number. But we know that mining is important. We need to continue to extract metals. We will each use approximately 1.6 million kilograms of minerals, metals and fuels in our lifetime. So is there a way that we can continue to extract the metals, but do so in a less invasive manner? And this is actually an image of an in-situ recovery mine. It would be quite easy to believe that the field has lots of beehives scattered along the surface, but those boxes are actually the wellheads to pump fluid underground for metal extraction. And I'll show you a schematic on the next slide that explains this in a bit more detail. So essentially, in-situ recovery involves the injection of fresh leaching agent or lixiviant or solution underground into the region of interest where the value is in the deposit, the dissolution and the dissolving of the value metal and also gangue minerals, and then the pumping of this fluid back to the surface for further processing. And the further processing at the surface is often by conventional means. So for example, solvent extraction and electrowinning. In-situ recovery is also called by a number of different names. So in-situ leaching, solution mining, in-situ metals leaching, invisible mining, and probably my favorite is keyhole mining. So we liken ISR to keyhole surgery, but in a mining sense, because the aim is to be as little, not to be invasive at all. So like you would have keyhole surgery. This is a diagram from the Gunnison Copper Project Technical Report Pre-Feasibility Study, and it shows how, and essentially how an in-situ operation would work. So you've got active leach solution that flows into these injection holes in orange, and the green lines represent the copper-rich pregnant leach solution in this case, which is pumped back out from underground to the surface from the extraction boreholes. And there are a variety of different configurations that the well field can be laid out in. Usually you have a central extraction borehole and a number of surrounding injection boreholes, and often more fluid is extracted than injected. So there's a continuous drawing in of fluid towards the extraction borehole, and that minimizes flow to peripheries outside the region of interest. There are also usually monitoring boreholes that are placed around the mine, and that's to prevent or to monitor and check whether any fluid is moving out of regions of interest. And the PLS at the surface goes to solvent extraction and electrowinning for the generation of copper cathode. So that happens during the active leaching phase, and then that's followed by a rinsing phase, which is essentially the phase during which the deposit is flushed out. Now, because sometimes external water, groundwater, is drawn in to form this cone of depression, the drawing in of the solution to the extraction boreholes to prevent the movement outside the region of interest, there is additional water treatment that may be required. So these are some photos of ISR sites around the world. The images on the left are from the Heathgate mining operation in South Australia. So Heathgate is a uranium mining operation, and you can see the impact. The actual picture of what the mine looks like is quite plain. You've got these pipes that spread out to fields, and at the fields you've got the injection and extraction, so the well heads. This shows one of the pumps in cross-section with the casing removed so that you can actually see what's inside, but it's quite plain and simple. This is another example of a barn in South Australia. It was also a uranium trial operation. And then you have these little plants where where you can control the flow, so the injection and the extraction. This is a colleague of mine, Norshad. He is standing at the Florence Copper well field in Arizona. So Arizona has a number of copper porphyry, there's a copper porphyry deposit belt, and there are a number of potential ISR operations. The Gunnison copper operation exists there, and Florence copper operation exists too. And they're making good progress in establishing the technique for copper oxide material. So in the copper porphyry deposits, there's usually an oxide layer at the top and the sulfide material at the bottom. The oxide layer is often very fractured and has readily accessible copper that's also readily and easily leachable simply with acid. So a lot of these operations are targeting the oxide minerals as an easy win. Now, ISR is actually not very new. There are references back to 177 BC and reports of copper recovery in China in 907 AD. ISR has been applied to water-soluble salts and also to certain minerals that are usually found in very porous and soft rock deposits. So uranium is a prime example. Uranium often exists in sandstone type deposits, so there's a lot of, it's easy to get flow through these deposits to recover the uranium. There's been limited uptake for ISR for the deep hard rock mineral systems. And this is mostly because of access. So in these very hard rock environments, you don't have flow paths to pump solution to the mineral of interest, and that obviously doesn't make a process such as ISR viable. So this slide is an image that was prepared by Max Soretkin, and it shows the history and the current situation with regards to uranium in situ recovery. So approximately 50% of total global uranium is actually derived from ISR. And that comes from the countries highlighted in orange, so Russia, Kazakhstan, China, Australia. And there have been other countries that have tried or trialed in situ recovery for uranium mining, and some that are planning to use in situ recovery. And the countries in green show those countries that use conventional mining currently. Other commodities have been trialed or are in operation. So Russia, for example, use ISR to mine gold, copper, nickel, etc. And there have been trials of other metals in other countries. But as you can see, the uptake is not very high. And as I mentioned, that's because of the matrix permeability. These metals are often located in hard rock. The other issue is the potential refractory mineral nature. So I said that in Arizona, a lot of the copper oxides are being targeted. The copper sulfides tend to be more difficult to leach, so they are not regarded as very favorable at the moment to process by ISR. And then, of course, a lot of these minerals are very broadly disseminated. So if they're difficult to access and not all located closely together, that's another reason why ISR might not be very advantageous. So onto the drivers for ISR. There are two main drivers. One is economic and the other is related to environmental safety and sustainability aspects. And if we look at the conventional mining economics versus the in-situ recovery mining economics, you can see that for a contained metal value in a conventional process, you generally would recover quite a high percentage of the metal. Usually it's impossible to recover or derive all metal value from a deposit. But you have your mining costs, comminution costs, concentrate production costs, and from the difference between the revenue derived from the metal recovered and the costs, you generate an operating profit. Now on the ISR mining economics side, for a similar contained metal value, it's very likely that you will recover a lot less of the metal because an ISR process is innately more difficult to control. However, you don't have the associated mining costs and comminution costs. So you do still have drilling costs and the costs required to establish a well field, reagents, etc. But despite the metal recovered being lower, there is still the potential to generate an operating profit by using the ISR approach. So that makes it potentially very attractive, especially for low-grade deposits. We did a bit of a calculation to assess the potential opportunity for ISR in Australia. And this estimate was based on the total sub-economic and inferred resources that are classified according to the JORC code. So we looked at the tonnages of the gold, copper, nickel, and uranium in Australian sub-economic and inferred deposits and estimated what the value of these deposits could be. And you can see in the red figures, this is of the order of hundreds of billions of dollars. Now, we don't think that all of these deposits could be processed by ISR, but if only a portion of the deposits could be, it still represents a significant potential value that could be derived from using such a process. So on the environment, safety and sustainability side, ISR has the potential, as I showed you earlier in some of the images, to reduce land disturbance, and there is much less permanent infrastructure that remains. So this provides an opportunity to reduce legacies, easier closure, and provide easier remediation. So instead of the large open pits and the waste dumps, potential subsidence from blockade mining and tailings dams, you essentially could have a field with a bit of infrastructure that needs to be rehabilitated, and obviously underground workings would need to be flushed. Because of the reduced comminution and mining costs, there is the potential for reduced energy consumption and greenhouse gas emissions and the associated dust and noise. And then there's also the option of removing operators from the interface, so that could increase the operator safety. Another important factor that's been highlighted is the potential for competing land uses. So if you were to mine, you could then farm subsequently or use the land for real estate. And ISR also has the potential to provide a lower capital entry for smaller players or junior players, because there's the option to scale up. So as you develop your well field and derive or generate value or generate income, you can scale up to larger well field patterns. And there's also the potential for modularization. So making a smaller plant that could be moved around, the option for remote operation, automation. We've spoken about use of renewables, potentially using solar, and you can pump during the day and let the fluid be dormant at night. So lots of potential exciting opportunities that could be added onto processes in ISR. I'll move on now into the research areas that we've been working on. And a number of years ago, we started looking at some of the challenges in various different areas, and there were many. So we tried to categorize them into social and environmental, economics and techno-economic modeling, resource characterization. It's very challenging to be able to characterize hundreds of meters under the ground when you actually can't see, and we don't really have tools to enable us to do so. The challenges related to creating, measuring and sustaining ore porosity and permeability, drilling, blasting and rock access. We have spoken quite a bit about different lixivian systems. So how can we improve the activity and the selectivity and reduce the environmental risk of the lixivians that we use? There are challenges around solution management and reactive transport modeling, and similarly around groundwater management and hydrogeology, and then monitoring and forecasting. Again, because it's difficult to see what's happening under the ground, how do you monitor your solution conditions, for example, changes in your mineralogy with time? So from this, these groups of challenges, we've distilled the three key technical components. The first is containment and hydrogeological control. You have to be able to control the fluid within an ISR environment and prevent solution losses, mostly from an environmental perspective, but also from a cost and processing perspective. You need to have leachable value and good in-situ chemistry. So I spoke about the copper sulfides and how it is difficult to leach, for example, chalcopyrite. And thirdly, you need to have access to the value minerals. So if any of these components is missing, it's unlikely that you'll be able to have a successful ISR operation. Now, underpinning these key technical components is the social and environmental aspect. And this is actually critical. We tend to focus very much on the technical components, and if that works, that's all good. But in this sort of environment, you need to have the social license to operate. I think that's becoming important in many mining environments, and it's especially critical in an ISR environment. So what I'll do now is I'll talk about the research that we are doing in those three areas and also touch on the social and environmental aspects. We've just recently got approval to start a project looking at barrier technology for containment. This will be run together with Curtin University, based in Australia, in Perth, and specifically the Civil Engineering Department. So we'll be looking at organic and inorganic barriers. These are used very commonly in the mining industry. At cryogenic barriers, these have been used previously underground, and also at biocements. So the biocements are generated by bacteria. Often they might be a carbonate type material. And we'd like to see how we can extend the boundary or widen the pH range that we can use biocements over. So biocements are often used at the moment for repairing statues and in roads, etc. So we'd like to broaden that envelope and see whether we could use biocements, which could be an affordable alternative to some of the commercial products that are available currently. We had a PhD student, Evelyn Martins. She's just recently finished her PhD, but she was looking at electrokinetics. So electrokinetics is a technique where you use a direct electrical current to drive species through potentially inaccessible rock. So in her setup, Evelyn had 2 electrodes. She had a piece of rock located in a central reservoir, and she had leaching solution flowing through that rock. And the intention was to see how the how the system responded with and without the direct electrical current. So Evelyn essentially proved the concept. This work was done with Henning Prommer and Andy Furey at the University of Western Australia. And it's now being taken forwards in a number of different projects. So the interesting thing was, first of all, that we could drive fluid through what looked to be a very impermeable rock. But the containment is also one factor that can be attended to with the use of electrokinetics, because you can drive fluid in a particular direction and in that way maintain and control flow. A colleague of mine, Mike Trefry, he's now left CSIRO, but a number of years ago, he looked at the effect of injection and varying injection and extraction at different well holes. So pumping is another way that you can contain and control fluid. As I mentioned previously, this cone of depression where you extract more than you inject, that continuously draws fluid to your extraction well and prevents the flow of fluid outside a region of interest. But the injection and extraction can also be used very effectively to help with mixing. And then these images at the bottom of the slide are generated from work that Henning Prommer and Jing Sun did related to reactive transport modeling that we did for Cauldron Energy. They were looking at the potential for a uranium in-situ operation in Western Australia. So the reactive transport modeling allows you to not only determine the effect of varying concentrations, for example, to observe what happens with time, but it also allows you, this sort of modeling allows you to visualize the flow. So when you inject and extract, where do the solutions actually go? What is their reach? And this is based very much on the permeability of the deposit. That's containment. Onto leaching. That's very much the area that I work in and that my group works in. And we focused very much on lixiviant screening, because there's the potential to use more expensive and exotic reagents that might be used conventionally. We've looked at reagents that probably wouldn't be considered for conventional processing. We've looked at thiosulfate, for example. Thiosulfate is a potential alternative to cyanide. So cyanide would probably never be used in an in-situ environment for gold extraction. And the image that you see, the photograph on the bottom left, is a commemorative gold ingot that was from the first gold pour using the cyanide-free recovery method. So thiosulfate is a potential promising reagent for gold extraction in situ from an environmental perspective. We've also looked at more unusual reagents, ascorbic acid, acetic acid, methane sulfonic acid. Some of these are proposed as more environmentally friendly reagents. Some of them might be more palatable for general consumption. So if you talk about lemon juice or vinegar, that's more understandable to people. However, anything that you put underground that varies from the background is something that needs to be considered. So even if you were to put water into a saline environment, that's a deviation from the baseline, and that does need to be returned or restored to original conditions once mining is completed. We've also looked quite a bit at lixiviant stability and compatibility. So if you look at the image on the right, you've got the injection well, the fluid moving through the deposit to the extraction well, and you don't have the opportunity between the injection and the extraction well to control solution conditions. So you can't adjust your pH, you can't adjust solution potential. There's the potential that if the conditions are incorrect, you either precipitate dissolved value or generate other precipitates that could block flow, for example. So we've done, and just as another point, between the injection and the extraction wells can be spaced up to 20 meters apart. So it's quite an extensive distance often that you'll be pumping fluid over. So we've looked at understanding if we do leaching tests without pH and EH adjustments, what sort of response do we get? And whether certain mineral ore types are more compatible with different lixiviant systems, to understand if there's a good potential match between certain systems. We've also looked at a more fundamental level at the fluid-rock interactions. So often in the leaching tests that we do, we mill material very fine to liberate all the value minerals and provide the best conditions for extraction. But in practice, in an in-situ operation, you're going to be pumping fluid over long distances with potentially very coarse material. So Tanya Hidalgo, one of our PhD students, she was from Curtin University and is just finishing up her studies now. She focused very much on coarser particles, so looked at little cubes of approximately 4 millimeters on the side. And we were aiming to understand areas such as value mineral transformations and kinetics. So for example, if you start off with a chalcopyrite block, after a period of time, what does the chalcopyrite actually convert to? So what minerals, what is the sequence of mineral transformations that occur, and how long do they take? What sort of additional porosity or cracks are formed with volume changes? Tanya's work focused on deep hard rock deposits, and so that's why she looked at quite high temperatures for her work. We also looked at varying reagents, so for example, methane sulfonic acid and hydrochloric acid. And you can see in this image, what's very interesting is that the fluid moves along the fractures and the cracks. And in this case, for the hydrochloric acid, you can see that the rate of leaching was higher for the same period of time because more of the bornite in this case was converted to digenite. Tanya also looked at some of the reaction products that formed in different systems. So this is important because these reaction products have the potential to block channels, and different reaction products form under different conditions. So acagania, for example, in a chloride environment, some of the silica reaction products are also important. And we've looked very much at the reaction product character. So sulfur formation in a chloride versus a sulfate environment, where we found that the sulfur, the product layer that forms on the surface of the mineral tends to be more porous and therefore allows fluid access to the mineral surface. And this has been seen previously in other literature. And then interestingly, if you look at, for example, the chalcopyrite and the bornite, the sulfur layer that forms at the surface, the morphology is quite different. So you get a more amorphous type morphology in the case of the bornite. And all this sort of fundamental understanding is important to understand what leaching reactions the minerals undergo, what products are formed, what speed minerals are leached at, what reaction products are formed that could be generating precipitates and resulting in blockages, etc. And then on the accessibility side, we've looked at understanding, again, at a fundamental level, what's happening to the mineral particles. So this is actually a vanadium-containing particle. We studied this particle by computed tomography scanning, so CT scanning in 3D, and then by coupling the CT scanning with cross-sections, mineralogy cross-sections, we were able to identify which minerals had leached and the percentage that was leached. So this type of work, Belinda Godel, one of my colleagues, she's a whiz at this sort of stuff. And we could understand, for example, if you look at this particle 1 and particle 2, P1 tended to leach by a shrinking core type behavior, whereas P2 seemed to leach more homogeneously. And we believe that this is related to the grain boundaries and movement of fluid along the grain boundaries. And then Tanya looked at some copper particles, again, understanding what happens to, what are the mineral transformations of the copper mineral itself, what products are formed, and also, as you can see in the lower two images, what sort of cracks and access is generated as a result of volume changes with leaching. I mentioned Evelyn Martin's work on the electrokinetics earlier, and we have another PhD student, Elahi Karami. She's co-supervised by us. She's a Murdoch University student, and she's looking at ways to enhance mass transfer. So we have a setup now that is suitable for electrokinetics, but can also incorporate ultrasound and pulsed pumping. So these techniques we are hoping are things that can be applied to enhance the mass transfer at the surface and promote leaching and overcome some of the accessibility issues that we might face. We also have upcoming another PhD project which will focus on alternative access creation mechanisms. So there's a lot of work done around hydraulic fracturing. Hydraulic fracturing is used very commonly in the oil and gas industry. And hydraulic fracturing essentially provides or forms a planar fracture in the rock that allows fluid to then move in a plane. For our cases, hydraulic fracturing might not be sufficient. So the fractures for hydraulic fracturing are often located sort of hundreds of centimeters to maybe a meter spacing apart, whereas our minerals are probably, our value minerals are probably located at a smaller scale. So there is the option, for example, to apply blasting to generate the microfractures that are required for access. But we'll also be looking at microwaves, cryogenics, and high voltage. And we have a student lined up to start as soon as they can get to Perth. So I mentioned previously, underpinning all the technical aspects are the social and environmental aspects, and I just wanted to highlight again how critical these aspects are. We are working with a company known as EnviroCopper, and they are investigating whether it might be possible to process a deposit in a little town known as Kapunda. So Kapunda is located in South Australia, shown by the star on the map. And there was a mine in Kapunda, or there's a remnants of a mine. So this copper mine was mined in the late 1800s through to the early 1900s, and there's still quite a lot of residual value underground. It's quite interesting because Kapunda is the oldest copper mine in Australia and is set to potentially become the first ISR operation if the research indicates that this is a good option and if all stakeholders are happy to proceed. The residuals, this is the pit lake that's left at Kapunda, and you can see from the aerial view that the pit lake is located just outside the town. So you can see this pit from the road. There's a walking track around the pit. People walk their dogs. It's also an historical site, so they've got signs up that show you the mining that was conducted many years ago. So you can imagine that stakeholder buy-in and social license to operate is critical for ISR to be trialled at this site. So what we've done is we have social scientists that work, that assist within the minerals group, and we actually visited Kapunda. I presented on the technical aspects of the project, and we got feedback from stakeholders to understand any questions that they have, any concerns, and that very much drives some of the research. So we answer questions that people might want to know about, and also helps to identify what is required to build trust in the company that is intending to do the work. On the environmental side, I've just provided an image of a scorecard. So this is actually for the Gladstone Harbour, to monitor Gladstone Harbour environmental health. So Gladstone Harbour is located close to the Great Barrier Reef. And what they've done is they've drawn up for different zones an assessment of environmental health related, for example, to the water and sediment and fish and habitats. And there's a ranking from very poor to very good for each of these zones. So for Kapunda, what my colleagues down in Adelaide are looking at is to develop a similar sort of scorecard. There's a river to the south of the deposit known as the Light River, and they've done monitoring along the river. They're assessing where does the water actually flow, and based on the parameters that are important to measure, they will draw up a scorecard that can be used during potential mining and also after mining, and that should be accessible and available to the general public and to stakeholders so that people can observe what the environmental state is. And essentially the environmental is very much about risk mitigation. So we set a baseline and then we'll determine the baseline, and the aim is to make no change, and if there is going to be a change, what would the subsequent action be that is undertaken to correct the change? So I mentioned, I showed you the image on the left previously, which is the schematic of the pure in-situ recovery approach. CSR is part of Mining 3, and as an alternative or potential stepping stone towards in-situ recovery is a process known as in-mine recovery. I've mentioned some of the challenges, and it really is a challenge if you think about how do we create access in these very hard rock environments. So as I guess a hybrid between in-situ recovery and potentially heap leaching, we're looking at generating a fragmented silo underground. So material would be blasted, some material would be withdrawn to create a bit of space, and then fluid would be pumped into the silo and back to the surface for further processing. And this is termed an in-mine process. And as I said, it's a bit of a stepping stone and a hybrid between the pure in-situ recovery and a heap leaching process at the surface. I wanted to just highlight some of the capabilities that it's really it's great within CSRO, because I generally can pick up the phone and get hold of someone if I need help in a particular area. We have scientists that span from the mining engineers through to chemists, through to social scientists. And we engage quite extensively in a variety of ways. So we engage with government and industry and universities and research institutes. And that's often in the form of one-on-one projects, or it could be in the form of multi-sponsor projects or via federal and state funded projects. And I've just highlighted or put some of the logos of different organizations that we work with. But I also wanted to just highlight that the in-situ recovery space we've tried to make as collaborative as possible. CICERO doesn't think that we can do everything on our own. So we encourage and we've invited collaboration with other research institutes, organizations, companies that are interested. And we try and share as much of the information that is delivered as possible. We've got a lot of support from the Minerals Research Institute of Western Australia, MRIWA, and all the work that we do with them becomes publicly available and accessible. And in fact, the intention is to transfer knowledge that is generated in these projects to the broader community for more rapid uptake. And that's how we see it. If we can work together with others in developing the technology, it can get to market quicker and be provided as an alternative to conventional mining technologies. So that's pretty much it from me. If you'd like to stay in touch, you wanted to ask questions about any of the areas I've mentioned, or if you'd like me to include you on our email distribution list, I send out an email every 2 months or so, letting everyone know what we're up to, or talking about some of the general things that are happening around the world related to ISR. We also have an ISR wiki, and we have in the past attached presentations from conferences and workshops. We actually have partnered now with the ALTA conference, so we present an ISR symposium, a one-day ISR symposium in the ALTA conference, which is held in Perth, usually in May. This year it's actually moved to November, and it will be an online conference running in November, so it might be easier to access from all around the world. On the wiki, we also put up the update emails that have been sent out, information related to some of the technologies related to ISR and project information where possible. So with that, as I say, please get in touch if you'd like to do so. But otherwise, thank you very much for your attention.
Thank you very much, Lara, for a fascinating presentation. I think most of us are still dinosaurs in the age of making big holes and digging out the soil. So it's really refreshing to hear the developments in in-situ recovery. We have a number of questions that has been submitted for you. I think the first one that perhaps you could just address is, you know, one knows that you choose your geology as carefully as you can, but essentially you get what is there. So a question here is, what are the chances of groundwater contamination, you know, using these lixiviants that you have? Surely you cannot have perfect containment. I know you've answered this question really through your presentation, but perhaps you could just summarize the issues around contamination.
Yes, it's a very good point, and I think it's one of the critical factors that needs to be addressed in an ISR application. So there are a few methods that are used to prevent groundwater contamination. The first is actually attempting to match the groundwater as closely as possible to the lixiviant system. So for example, if you were operating in an environment where the groundwater is at a pH of about 3, you very likely would use a leaching agent that would be in the lower pH range. And similarly, if you were operating at a higher pH, you would aim to use, for example, a carbonate leach. So first of all, it's matching the groundwater as far as possible so that there isn't a big deviation from the background. Secondly, I would say would be to control your pumping regime. So there is the option, as I mentioned, to control the injection and the extraction wells so that you generate the flow, the required flow pattern that you want. And you have your monitoring boreholes around the periphery of the operation so that you can very closely observe if there is any issue with fluid leaking out into the environment. And then thirdly, I'd say is related to the mineralogy of the deposit itself. So often in the uranium operations, they have confining layers above and below the region of interest. So the mineral itself forms a type of barrier. And I remember a colleague of mine, he visited the Heathgate operation in South Australia, and he said that I think they worked out that if they did have any leakage of lixiviant, it would attenuate in sort of millimeters per year. So it would move out really slowly from the region of interest. And I think also this, linked to the mineralogy is an understanding of the natural fractures that exist in the rock before starting operation. So you want to be aware of those natural fractures. And the Kapunda operation in South Australia is quite an interesting one. So they've used core, so they've logged fractures and derived a fracture model from core logging. They've also used magnetotellurics, which allows you to see, to locate the fractures underground. And they've built a fracture model that then allows you to model the potential fluid flow and solution flow. So a combination of all these factors together is probably required to ensure that the groundwater isn't contaminated. And then I guess as that additional level, for example, as will be done at Kapunda, if the trial goes ahead, is that the groundwater itself is monitored. So the Light River sampling would be taken and to ensure that there isn't any contamination of groundwater. But that's definitely one of the factors that our minds move towards as a first thought, because it really is a very critical and important factor to consider.
Thanks, Laura. Another question that's come through is, obviously when one looks at the schematic, it looks simple, but we also know that it never is. So the question is, what determines the placement of boreholes in such a operation?
So at the Heathgate operation in South Australia, the borehole placement follows very much the uranium deposition. So the uranium is obviously deposited in rock that was quite permeable, and there was preferential flow in certain directions. So they characterize where the mineralogy is, and then the wells or the boreholes are actually placed along that mineralogy. So they follow the flow of the ore itself. I don't know exactly how you would determine whether you have for example, because they have 5 spot wells where you have a central extraction well, 4 surrounding wells, you get 7 spot wells. So there are various configurations. The most common is probably the 5 spot well. But I think that can be arranged and modified to suit essentially where your value minerals will lie. The drilling costs for establishing a well field are probably the highest cost. So you would try and minimize the number of well holes that you drill, and you would try and maximize the spacing between the injection and the extraction wells. So it's a bit of a trade-off, because the closer the spacing, the more likely your fluid conditions will be unaffected, that you won't get your value mineral potentially precipitating out, for example. But the closer spacing that you have with your boreholes, the increased cost. So it's related to where the minerals lie and how wide apart you can space your boreholes.
Okay, Laura, the next one is really a question for you to cast your eye into the crystal ball. The question is, do you think the mining industry will reach a point where most minerals can be extracted in situ, thereby eliminating mining and comminution needs?
I think it will be a big challenge. Sometimes when I think about what we're embarking on, I think, oh gee, it really is a big challenge. But I think if we don't work towards it, we won't get anywhere. The biggest challenge, I would say, is the hard rock type deposits and creating access. I think in terms of a lixiviant, we probably, yes, could find something that could leach anything. I mean, you could use aqua regia potentially, although I don't think you would probably use, or you could use that maybe in an ISR environment. But even chalcopyrite, you can leach if you hit it with a big enough hammer. But then, for example, you might need to heat solution, which is costly. So it becomes a trade-off. It probably, yes, would be possible to mine anything, whether it's cost effective would be another question. So you could be heating fluids and providing solutions of high concentration. You could be using blasting to create good access in deposits. But the question becomes, is it cost effective to do so? Is it going to be too expensive to potentially blast everything to generate the access? Is it going to be too expensive to spend money on the lixiviants when the value that you potentially derive, if it's a low-grade deposit, for example, might not be high enough? So I always say if it doesn't disobey the laws of chemistry, physics, and maths, it's possible. So yes, I think it's possible. Whether it's economically feasible would probably be another question. So I don't know if we'll ever see a complete move to ISR. I think there are also a lot of other developments in conventional mining to reduce impact, and I think we definitely will see a lot of those in conventional mining too.
Thanks, Laura. I think you've mentioned something earlier about, in one of your slides about recovery, but there's a question here about the volume balance control in ISR. They want to know, is it well controlled? And what type of volume recovery are you normally looking at?
So when you say well controlled, is that in the sense of leaching, or is this the fluid control?
It sounds like the question is about the fluid control and not necessarily the value elements control. So it's essentially, it looks like you know, how well is the fluid actually taken through the system?
Okay. So unfortunately, I don't have actual values, but from what I understand, I think it is very good or pretty good. I don't know if solution is lost. I think often because in-situ recovery is actually conducted best if it's in a saturated environment. So in other words, if you're working below the water table, because if not, if you pump fluid into an unsaturated environment, it tends to disappear. That's where some of the barrier containment thinking comes into play. Are we able to actually block off and isolate regions? So I don't have any figures offhand, but my perception is that the volumes that are injected are extracted, and sometimes even more is extracted because surrounding groundwater is actually drawn out with the extraction fluids. So unfortunately, I don't have a number, but I suspect that the volume control is very good.
Thanks, Laura. Another interesting question that's come up there, I guess, you know, we've heard a lot of, especially in South Africa also, about fracking. So the question is there a place for fracking in this process, and aren't you actually doing that already?
Yeah, I've learned a lot about fracking over the last few years. We've got colleagues in Melbourne who, within the energy group, and they do hydraulic fracturing. And so a colleague of mine, James Keir, he puts up a picture where he shows what fracking is and what fracking is not. And he shows a picture of almost a tree with lots of branches, and he says that's not what fracking is. Fracking is essentially a plane that is formed. But there is a lot of concern about fracking and potential contamination. And I think fracking has a place in ISR, but I think because the mineral dissemination is probably much more closely spaced than what the spacing that a fracture could give, I think that fracturing might not be sufficient in an ISR application. I think also if we were to use, so colleagues of ours do research on fracking for mostly the energy, oil and gas environments, but I think that's why research is so important. They are looking at, for example, notching, so they drill boreholes and they notch the boreholes so that they can generate fractures that are very controlled. They do the notching to allow spacing of the fractures so fractures don't intersect and stop. And interestingly, when they do the fracture it's not a very sudden release of energy. It's actually a very controlled release of energy. So the fracture moves out from the borehole at sort of a walking speed. It's a very slow and controlled process. But I always say we want to do things as safely as possible. So we need to do the research. We need to understand hydraulic fracturing. We aren't using hydraulic fracturing we're not really studying hydraulic fracturing in our ISR at the moment. well, actually, I should say, colleagues of ours are looking at ISR fracturing for application to ISR, but I think that we're going to need more than just hydraulic fracturing. And if we do use hydraulic fracturing, we need to do the research to understand that we can do it safely.
Laura, again, just perhaps a bit of a crystal ball question from me as well. I've seen that you had a few slides on the different things that one can do, like electrokinetic driving of lixiviants, for instance, through material, as well as a fascinating combination of underground heap leaching. How much do you think that would advance this sort of approach in the mining industry compared to having just to rely on what nature gives you?
So the challenge is, I think, when you look at these more sophisticated techniques, is how to embody them at a larger scale. And we're at the stage, for example, of the electrokinetics and the microwaves, the ultrasound, etc., where we are very much proof of concept. So we want to know, that will this actually work? Does it help? Does it make things better? And then the next step up is to see whether it can be upgraded and used at a larger scale. I think the applications of the cones, the crushed underground heap leach equivalent, is a really good example of moving us closer, one step closer towards practical implementation and uptake of the technology. And it often just needs a test case, a site that it can be tested at. Many companies don't want to be first cab off the rank. They prefer for someone else to test it first before it gets implemented. But that's why I think it's great to be able to do these projects within the research space and prove up some of the techniques before it can be shown to be viable or not. And then that could move into more of a production zone.
Laura, then there's another question. There's another question here, going back right to the front. If you have say an ore body and you are considering ISR, where do you start? Where would you start in terms of laboratory work and the different steps until you get to a point where you can make a decision on whether to go this direction or not?
Yes. So what we tend to do is we look first of all at the mineralogy, so characterize samples and understand what is there. And then we move to leaching tests. So usually bottle roll leaches on finely ground material to understand what are the best recoveries that you can get with a chosen system or variety of lixiviant systems. And once you've established that that's possible, you start moving to scale up. So the scale up to column leaches, for example. In parallel with that, it's important to understand the fractures in a deposit. That can be done, for example, through core logging, so understanding the fractures in cores that are drilled out of the ground. And often modeling can be done, so the images I showed from the reactive transport modeling, that was done based on permeabilities of cores. So that enables you to see whether you will actually have the conductivity that's required in a deposit. So it's do you have the access? Is the deposit permeable enough? Are you able to leach it? And are you able to contain it? So those three key technical components. Once you've worked out or have an idea of the mineralogy, the leachability, the containment, the permeability, so how the solution will flow through a deposit, it usually would move to a field trial where you would drill just a few boreholes and then see whether the reality, so what you actually extract, matches what your predictions were and whether such a process could be feasible. And that's often would be linked to an economic evaluation. So depending on the kinetics, so you get leaching kinetics from the laboratory, and you could confirm that in the field and link that back to whether the deposit or the processing of such a deposit as a whole would be profitable by in-situ recovery. So it moves, I guess, from lab scale to field trials, and from there to potentially larger operation.
Given that one one pumps a solution aimed at dissolving material through, through your deposit. What is your view on the competence of the ground conditions post this in situ recovery process? Have people found that subsistence is a major issue at all during this?
Yeah, that's a very good question. In fact, that came up in one of the focus groups in Kapanda and directed our research towards looking at overall mass loss as well, because that is a perception that you potentially could dissolve away a lot of the rock and get the ground subsiding. Generally, we found that the mass loss overall is very low. Often the materials that we work with contain a lot of quartz that is unleachable. So the deposit itself, you might leach 1%, or in the very small percentage range of material, and it's unlikely that you would get subsidence. But if you, for example, found that you had a very high percentage of the material that was leachable, and that with time you could essentially dissolve away the ground, yes, that would be a red flag. But in general, a lot of the deposits that we work with consist of a lot of waste rock, which is unleachable, and then a smaller percentage of value. And that also presents the challenges, because if you have gangue or waste mineral that is leachable, you potentially can access additional value. But if you have gangue that you can't leach and you can't create access through, you sometimes can't access your additional value. So yeah, that's a really good question. We think that there wouldn't be a lot of subsidence unless you have an unusual deposit where a lot of the minerals are leachable.
Thanks, Laura. As you know from the diamond industry, diamonds are spread through the kimberlite, and it's not always known exactly how. But the mine plan often called for mining in different areas to balance the feed to the plant, for instance. Is it possible? There's a question here. Is it possible that one could do the same thing, balance your process in such an in situ recovery operation by pushing, for instance, more flow through areas of higher concentration, if need be, to balance your feed more?
Yes, definitely. And I think that's part of the beauty of the in situ recovery approach. You don't only have one pit or very fixed underground workings. You have the potential to switch regions of the well field on or off. And in fact, I've seen models where I think it was developed for the gas industry, but they are able to monitor very carefully the interaction between the boreholes and identify if they were to switch one on, what the effect might be on the surrounding region. So yes, that would be part of the control during operation, and would be managed obviously to minimize potential reagent consumption and maximize value extraction, and to help in flow control. So yes, that's, I think, definitely a possibility.
Okay, and another question here is obviously miners often look at the costs. The question is, how much water and power is required for such a process?
Oh, Leon, you got me there.
This is a bit difficult to answer, because it really depends on what the conditions are, and so. Yeah. But if you can perhaps just give a general view.
So I think, because I unfortunately I can't give you numbers. Actually, I wouldn't know off the top of my head. But there is the costs, for example, for the mining and comminution should be significantly reduced. You would have to drill your boreholes. So I think from that perspective, there really is an advantage and a potential for reduced costs. And from a water perspective, essentially you've got a closed system. So you're pumping in and extracting and just reusing whatever water or lixiviant system is available. You would have to top up lixiviant, but because it would be a closed system, I would imagine that your water consumption overall should be low.
Okay, thanks. I think one of the last questions here that we've received relates to a potential application of ISR in alluvial deposits. For instance, in tin. The question is ISR only fit for primary deposits, or do you think one can also apply it in alluvial deposits?
So I think I'm assuming, I don't know very much about tin deposits, but I'm assuming when you mean alluvial, it would be very porous permeable type deposits. Would that be the type of deposit, do you think?
Yeah, I'm not sure. I think, you know, as I see ISR, it's all about containment. I mean, you don't just want to pump something through and it goes. So I guess you have to look at exactly what this deposit looks like. And if you also remember the West Coast diamond mining, you know, you often have quite solid bedrock and you have these alluvial deposits in these channels.
Yes.
I guess those could be potential applications.
Yes.
But surely it would depend on what is around it.
Yes, so I think I was thinking, so I'm not familiar with tin necessarily, but I was thinking of the gold paleo channels. So these are essentially old riverbeds, and gold was transported down these rivers and then deposited along the rivers. And paleo channels potentially could be an excellent opportunity for in-situ recovery because you potentially have very good permeability in these deposits, and perhaps the tin alluvial deposits would be similar. And then, of course, you need to look at the containment, but if there's, as you say, impermeable bedrock at the base and potentially confining layers or confining minerals on the sides. And again, you could use the actual injection and extraction, the pumping to help control flow. But the higher the permeability in a deposit, the higher or the more advantageous it might be to use in-situ recovery. And especially if by natural deposition, basically reversing the forces of nature, if you have access to where nature deposited the minerals, you could reverse that and extract the minerals from those regions as well.
Okay, Laura, the last question that I have in front of me is really related to the deposits and how complexity of the deposits impacts on the application of this technology.
So would that be complexity in mineral type, do you think?
Yes. It says here, for example, folded or intensively faulted deposits.
Okay. I'm not sure what a folded or intensively faulted deposit is, but I'm thinking it maybe relates to two factors. The one is the mineralogy. So if you have, it depends very much on how leachable the minerals are. So for example, in a copper deposit, so for example, a porphyry copper deposit, you've got your copper oxides, very readily, easily leachable. You've got your secondary sulfides, so your covellite, chalcocite, for example, relatively easy to leach if you add a bit of oxidant. And then you've got the more difficult primary sulfides like the bornites and the chalcopyrite, which is difficult to leach. So depending on what mineralogy you have, if depending on the range of mineral types that your value metal is located in and how leachable they are, that would obviously dictate whether that's possible. And then just in terms of the faulted question, I'm guessing that's related to the access, or maybe not, but it would probably link back to access. So the channels or the fractures that you have, are they going to the right points? Are they reaching the value? And are you able to then direct fluid to the minerals of interest to dissolve them for extraction?
Okay, Laura, thanks very much. That seems to be the last of the questions. Once again, from me, thank you very much for agreeing to do this presentation. I personally really enjoyed it, and nice hearing from you again. And yeah, so I guess if any more questions come, you've given some contact details on the presentation. The presentation will also be made available. So I can just say to everybody that please contact Laura if you have any specific questions about this. I'm sure she'd be happy to answer them.
Yes, no, definitely. Thanks, Leon. And thanks again for the opportunity. It was great to chat with you and also to present on this work. And yeah, I hope I hear from some of the attendees in the future. Thank you.
Okay, thank you, Laura.
All right. Thanks, Leon.